Hello everyone, it's January 22nd. Finally, it's a clean slate. We got rid of all the other problems. Okay, so we can start fresh. Find the town judge. In a town, there are n people, labeled from 1 to n. There is a rumor that one of these people... Hold on, I have my cat meowing. Alright, got it. Successfully dealt with the cat. Okay, there's a rumor one of these people is secretly the town judge. If the town judge exists, then the town judge trusts nobody. Everybody except for the town judge trusts the town judge. There is exactly one person that satisfies properties 1 and 2. You're given an array trust, where trust I representing that the person labeled AI trusts the person labeled BI. Return the label of the town judge if the town judge exists and it can be identified. Return -1 otherwise. Alright, so we're saying that the town judge trusts nobody and everybody else trusts the town judge. So we're saying this is going to be a graph. Alright, so AB is going to be edges. A trusts B, so 1 trusts 2. So 2 is the judge. And in the second situation, 1 trusts 3, and then 2 trusts 3, right? Okay, in the last case, 1 trusts 3, 2 trusts 3, but 3 trusts 1. And then that's not possible. So basically, when you find the node that everybody else points to, n equals 3, right? Everybody points to. And if none of this exists, then we don't have. So how would you do? So everybody needs to trust one person, right? So in this list, if everybody needs to trust another person, and then we have n, and the size of trust is equal to n, then that's not gonna be true because the judge cannot appear at the left hand of this label, of the edge. So the trust must be n-1 in size. And then we can just go through the trust and see who is not named on the left hand. And that must be the judge. Well, of course, on the right hand, everybody should be the same. So what we need to do is collect the left. Make sure the left is, we can do a set when I collect on the left, right? And the size needs to be n-1. And when I collect on the right, and the size needs to be 1, and that number cannot exist on the left. So that's how we can do. Or actually, it might be a little bit easier. We just collect the left and see something is missing. Right, if let's see who is missing on the left. What would be the best way to handle this? So we look at the first one, we already know who potentially the judge is, right? And then all we need to do is, we still have to get a set on the left and we get a set on the right. And make sure the set on the right is size 1, the set on the left I don't like how this one sounds like, but that's how we're gonna deal with this one. It doesn't look elegant, this solution, but definitely works. So we can say the people is going to be a set. Judge is going to be a set as well. Of course, we say if len trust. I mean, we might have all pairs of trust are unique. So yeah. So if len trust is larger or equal to n, that's going to return -1. Otherwise, we say for AB in trust, people dot add A, and then judge dot add B. Then we say if len judge is equal to 1 and len people is equal to n-1 and list judge 0 is not in people, that will return list. Oh, we can do this. J. We can return J. Otherwise, we'll return -1. Okay, let's try this. I mean, yeah, that's fine. Okay, let's try this. Oh, let's take all of them. Okay, let's give it a shot. Let's see if it works. Oh, doesn't work. The hell? So confident. Oh, hold on. Town judge trusts nobody, and everybody except for the town judge trusts the town judge. But it doesn't say everybody has to trust the town judge. Alright, so that's my misunderstanding of the problem. 1 trusts 3, 1 can trust 4. It's okay. So it's going to be between 3 and 4, right? 2 trusts 3, and 2 trusts 4. So it'll be 3 and 4, and 4 trusts 3. So the answer shall be 3. I see. So this is not right. So basically, we'll do this, right? It doesn't matter. So we have potential judges, right? And then we shall go through the potential judges, and there shall be 1. We're going to say for J in judge, if J, we need to know who is the judge that's left. Minus. Can I do minus on the set? Can I do, say, A equals set? I don't know. 1, 2, 3. B equals set 1, 4. Right? On the A minus B. A minus B. No. How about B minus A? And do B minus A. The judge minus. So we can do judge minus people. So if any that's in the people will be get out. And then truster and trustee. Okay, so these are truster. And then this will be trustee. Trustee. Right? And then trustee minus truster is going to be judge equals this. And if len judge is equal to 1, then we return list judge 0. Otherwise, we return -1. In trust, find judge. In trust. Okay, let's try this one. Yeah, I misunderstood the problem. Okay. No, I don't want to do this. What the hell? One trust two, two trust. Wait, hold up. 1, 1, 2, 3, and 4. Three people. That should be -1. Because 1 trusts 2, 2 trusts 3. But everybody should trust the judge. But nobody trusts the judge. 1 trusts the judge, 2 trusts the judge, 4 trusts the judge. Holy crap. So the truster need to be 1 to 2 and 2 to 3. That's not right. Huh. Yes, so we need to find a node. We can reverse it. If we reverse it, we just need to know who has. Okay, if we reverse it, I see what you're talking. We reverse it, and then we count the neighbors, the number of neighbors. So one node must have the number of neighbors that's equal to n-1, right? That's cool. One node needs to have n-1 neighbors. And this one cannot be in the trustee because he doesn't trust anyone. So we'll do something like this. So we have trustee. We don't need truster. So we need a graph of list. Okay. Right. So I have trustee. No, truster. Only truster. So truster do this, but graph we say b dot append a. Right. And then at the end, we don't even need to append. We don't even need to append. We just need to say a counter, right? Oh, we can just say a counter. This is just basically a counter. We can say a counter. So number of trustee counter, right? Now we just say trustee counter b, right, plus equal 1, and then we need to find right, and then we can say judge, right? And then we say if trustee counter b is equal to equal to n-1, then judge dot append b, right? This could potentially can be a judge, right? And b is not in truster, right? It cannot be a truster. No, we'll do this at the end. So we do this, and then potential judge. So they all have n-1. So you cannot have two judges, right? So you have one. So we say if land judge is not equal to 1, return -1, right? And then or judge 0 is in truster, then we return judge 0. This shall work. This shall work. Come on. Can't believe an easy problem you have to error twice. Yeah, this one shall be right. Oh my god. 3 times. Dude, didn't check that. What's this? This is nobody. Nobody trusts anybody. No, expected 1. Wait, what? Trust length. So we could have one person. If it's one person, then that person is the trust. So no here. So if judge is equal to 0. Is that a special case? Because we don't have anybody to trust. There's nobody. Nobody is in the trust. So how am I deal with this? What's this situation? So nobody trusts anybody, right? If nobody trusts anybody, then we have that's a special case. Well, hold on. If this is larger than, we have more than 1, right? Then we need to figure out a case and say if not judge, right? If not judge, there's no judge. There's no potential judge. Now, if there's no potential judge, so no one received more vote, and that should be null, right? So I think this is a special case at the front. So if not trust, and n is equal to 1, so return 1. Should just not equal to 0. It's just for that special case. How? Wait, what is the right way to solve this? I got it wrong 3 times. And that's terrible. What was the solution for this? This is as bad as it can get. Unbelievable. Full scrambling together a passable solution. What the hell? How would you solve it? Let me think. Maybe we do have to use a graph. I mean, I am using graph, man. I am using graph. You can say start from, we start from 1. Start from 1. But we might have multiple people. Wait, will we have multiple people? Yeah, we could. We could have multiple people that have... But the thing is, I don't have... Dang it. Now what I can do is, instead of doing this, okay, yeah, and I don't even do this. I don't even do this. I have the trustee counter, truster. Now we do this, and then we just say for I in range 1 to n plus 1, okay? And then we just do judge, right? So if trustee counter I is equal to n minus 1 and I not in truster, judge dot append I. And then we say if this is not equal to, return, otherwise return this. That is more generic. Yep, this one is more generic. Alright, how did we do last time? Explicitly considering and the edge case. I don't know, honestly. What method did I use? In degrees. In degrees. What's the original solution? Potential town judges. I use a counter. That's actually a good way. Yep, that's actually a good way. In degrees. In degrees. I see. In degrees plus 1. The town judge has in degree of n minus 1. Also, if for a truster, its in degree must decrement by 1. So in degrees equals, let's not open this. Right? What the hell? And then for AB in trust, in degrees B plus equal 1, in degrees A minus equal 1. And then for I in range 1 n, right? 1 to n plus 1. If in degrees I is equal to n minus 1, then we can return I. Otherwise, we'll return minus 1. That shall work. Yep, in degrees. All right, let's move on. Oh, got more. It says categorize box according to criteria. 4 integers: length, width, height, and mass. A dimension of and a mass of a box, respectively. Turn a string representing a category of the box. If the box is bulky, if any of the dimensions of the box is greater or equal to this, or the volume of the box is greater or equal to this, the mass of the box is greater or equal to this, it's heavy. It's both bulky and heavy, and it's both. If neither, it's neither. Box is bulky but not heavy, it's bulky. If it's heavy but not bulky, it's heavy. Oh, okay. Well, I haven't done LeetCode for a long time. I haven't done these things. 25. I think we just follow it. If any is larger, so we need to do the volume, right? Okay, so is bulky to any of, length larger is greater or equal to 10 to the 4. Yeah, that's okay. I'll just do this. Width larger equal to 10 to the 4. And height larger equal to 10 to the 4. Any is greater or equal to this, or the volume is greater or equal to. So the last one is length times width times height is larger or equal to 10 to the 9th. So let me rearrange this thing. Okay, so that's the first condition, is bulky, and is heavy is equal to box is greater or equal to 100. If the mass larger equal to 100. And then if is bulky and is heavy, we'll return both. If not is bulky and not is heavy, return neither. Right? If bulky is bulky, and if is bulky, return bulky, and the last one will be return heavy. Okay. It's heavy. Oh, what do you do? If heavy. No, if is heavy. Okay. Okay. Alright, question number 2. Find consecutive integers from a data stream for a stream of integers. Implement a data structure that checks if the last k integers passed in the stream are equal to value. The last k integers passed. Data stream disinitialize the object with an empty integer stream and 2 integers value, k and value. Put in consecutive, add num to the stream of integers. Return true if the last k integers are equal to value and false otherwise. Hold on, what do you mean? What's value? Value is 4. K is 3. Oh, last 3 integers, are they 4? Consecutive integers. Now I got it. So consec 4 adds this. So we start with 4, 3 with nothing. 1 integers return 2 integers. Oh, so also false. 3 integers. We say the last 3 integers are 4, and the last 3 integers is this. So k is this, right? So we need to keep k, right? We'll keep k, and every time we add 1, we'll pop 1. We add 1, we pop 1. That is fine. We can use a q for that. And then once we add a new value, then how do we tell that they are all the same? We can use a set, right? We can use a set. So every time we remove, set is not going to work. We had this one before. A counter. We need to use a counter, right? So every time remove, we'll remove. And every time we add, and then we'll check. We will check the counter to see what's what. And we'll have the total value, the total count. So we don't have to keep all 10 to the 5th values. No, that's not necessary. We just need to see that the size of the counter becomes 1. Yeah, so the new one comes in consecutive. When new one comes in, right, if the size is this, then we need to pop. Oh, but who do you pop? Who do you pop? We do still need to keep k, because we need to know who to pop. All right, otherwise how do you know who to pop? You don't. You need the order. So we still need k. That's all right. I think we will not run a size limit. I think it should be fine. So we need a counter, okay? From collections, need to import a counter. So we just say self.counter equals counter, all right? And then we need to do a deck. What if you don't have a deck? If you don't have a deck, because you keep adding, you can, you can do, holy crap, do you want to try that? We can design a circular queue. It's possible, but I don't want to. That's all I want to do, okay? So, simple as that. Then we just add one, right? Self.queue.add, not append, num, okay? And self.counter num plus equal 1. If len self.queue is smaller than k, return false. Right, and then if len self.queue is larger than k, right? If it's larger than k, then we need to say p equals self.queue.pop left, and then self.counter p minus equal 1. If not self.counter p, then we'll delete it. So delete self.counter p. Well, we can pop. We can say self.counter.pop. Say pop p. Right? Actually, I'm not 100% sure. Pop 2. Yep, that's right. So I'll pop it. All right. So then maintain its length is k, and then we need to see. We just need to return true or false, right? Yes. We just say return len self.counter equals 1. That I think shall do. Shall do. I only have one test case. K is not defined. Forgot K. Okay, I think this should be right. Let's just try this. Come on. Oh, the heck. Search 2 is false. If that's 1, oh, what the hell, man? And Lord, it has to be equal to the value. What happened to you, man? Don't read the problem. Like, you haven't even used value yet. Don't read the question. Don't even do this. Come on. List self.counter.keys 0 equal to. Nah. It's self.q. Because it's always 1, so equal to self.value. That should do. Like, Jesus. Imagine this is actual contest. You make stupid mistake like this. How are you gonna how are you gonna feel about this? Huh? How are you gonna feel about this? Being so stupid. I don't know how I feel. I'll feel very bad because it's such an easy problem. I actually think this is easier than today's quote-unquote easy problem. Oh, the performance is terrible because we kept It's a very naive solution, but it works. However, performance is terrible. Well, we're talking about consecutive, right? So maybe the queue, if it's consecutive, we don't have to keep, but then you need to know how many there is when you pop. Holy crap. I mean, we can have 2, right? We push in 1, push in again, different, 1, push in again, different, and then if it's consecutive, we just increment. Consecutive, we increment, and then we pop. So eventually, you know what? I do think this might be a better solution. Hold on. Yeah, this terrible performance. I don't like it. Q shall accept shall have each element in the queue shall be value and then count. Okay, so I don't need this. I do need these two. And then I'll say if not self.q or self.q, the last one 0 is not equal to num. Then we say self.q.append num 1. Okay. If it's smaller, then false. If it's larger, then we need to check, right? How do we check? We say self.q 0 1 minus equal 1. If not self.q 0 1, then we're gonna pop it. Self.q pop left. Okay, doesn't matter, we just pop it. And then we return len self.q equal to 1. Oh. We do this, and then self.q minus 1, 1 plus equal 1. And now this is equal to 1, and self.q 0, 0 is equal to this. Okay, so this, I presume, shall be, well, at least slightly faster, I hope. But hold on, we'll do both test cases. Let's see. Interesting. First one is not right. Okay, let's debug what happened. If not self.q, we append this, okay? And then the last one, so it will be 4, 1, right? Oh, the length. Oh yeah, the length is not right. We should not do the length. We shall show shelf dot count 0. Okay, and every time we do this, then self.count plus equal 1. If self.count is smaller than k, blah, blah, blah. If self.count is larger, then self.count minus equal 1. Okay, let's try this one. Oh, this one's correct. Nice. Much faster, but still. Much faster, but the percentage still abysmal. So, what are the good solutions you guys have? Just count it. Just count it. Oh. Ah. Screw me. No Q. K value count. If num is equal to self.value, self.count plus equal 1, else self.count equals to 0, return self.count equals k, right? I just have this problem today for whatever reason. Ew. What? Oh, the beginning. No. The last one shall be false. So we want value as 1 to appear 2 times. If it's equal to this, the count also cannot be larger than k. So equals maximum, right? Self.count plus 1 and self.k, the minimum of the two. Yep. I should put a minimum there. But still, huh? Just count it. Lord. But this is a little tricky. Okay. Yeah, I think this is just the initial solution. I didn't check. I think we have the same solution. Larger equal to. Oh, larger equal to. Yeah, larger equal to. That's the one. That's faster. Bad. So bad. Find exclusive all. Beauty of array. A zero indexed integer array. The effective value of 3 indices I, j, and k is defined as the effective value of 3 indices is or and. The exclusive or beauty of the array is the exclusive oring of the effective arrays of all the possible triplets of indices. Where this return the exclusive or beauty of nums. Bitwise or and bitwise and. So numbers this ijk can equal, oh holy crap, 0, 0, 0 is 1, 0, 0, 1, 0, 1, 0, 0, 1 is 1. I have 8, so 2 to the, since we have 3, right? I have 3 positions, and then we have 2 values, so each one can have 2, so we have 3, so 2 times 2 times 2, now I have 8. So, and this is 10 to the 5th. Each one has, the first one we can have 0, 10 to the 5th. So 10 to the 5th times 10 to the 5th, times 10 to the 5th, 10 to the 15th. Now, there gotta be some magic in exclusive OR and regular OR. Wait, expand this and see how it looks like, right? So that's actually a good example. We have two values, right? We have, we can just call it 0. So it'll be 0, 0, 0, right? Exclusive OR 0, 0, 1, exclusive OR 0, 1, 0, exclusive OR to the end. So if we get all the bits out, what we're doing is OR everything. So every value will be called upon how many times? Well, it's all possible triplets, right? So in the first position can be 0, can be 1, can be 2, right? So the first position can be all the values repeated how many times? I mean, it's all and the end. The last one is end. So all and all, okay, and that will be an end, and then exclusive all this. So what is the rule of exclusive all? That is a good question. I do not know. What's the rule of exclusive all? Exclusive all. Exclusive all. Associative? Is it associative? What's the commutative? It's both commutative and associative. Wait, what is exclusive all? Exclusive all is A and B bar plus B and A bar. That's exclusive all. Let me see. A and B bar. So B reverse. Okay, so B reverse 1 will become 0, 0 will become 1. Okay, so this will be 0. So this is 1, then they'll become 0 because this is going to end this inverse. This will end this inverse. Okay, but if they're different, 0 and 1, then we will end its inverse. This will end, it will be 1. I did not know that. Okay, this. The Morgan's law, distributed law, and expanded. I already forgot all these laws, man. Anyway, it's let's see this one. An intuitive way is associative. I mean, it's commutative for sure. Yes, I know it's commutative. Associative. Yeah, it's very simple. Associative is A exclusive of B. Wait, no, but that's not what my question is. My question is something exclusive or something. So we're talking about A or B and C exclusive or D and E and F like this. What is this? Well, we can follow. Oh my god, are you kidding me? We're gonna use these laws. So so this equal to A or B and C and D or E and F plus is just or D, E, F and A, B, C. All right, what's De Morgan's law? Completely give it back to the teacher. De Morgan's law. No, that's not what I'm looking for, right? Oh, this is or and. There we go. Wait, no, that's not what we want. Formal proof. Blah blah blah. No. I think this is good enough. This is basically saying A or B, right? Inverse will equal to A inverse and B inverse. And A and B will be A inverse or B inverse. Okay. So with this, so we'll first expand this. So this is going to be, we can call it D or E and F inverse. So that will be D or E inverse, right? Or F inverse. F inverse. The hell is inverse? Inverse is going to be just flip the bits, right? Inverse is just flip the bits. Okay. Inverse is to flip the bits. That's a tilde, right? That's a tilde. Okay, D or E inverse. That's gonna be D inverse and E inverse or F inverse. So we have A, B, C, and this thing. Okay, and we need a new thing. And or associative law. Associative. No, we want this. No, it's not what operator associativity. No. What's the thing you want to look for? Operator, logic operator. No. Actually, I don't know. Cumulative, associative, distributive. All right, that's just all this we need to. What we want is the Morgan's law. Now we want this. All right, so we know A or B, A or B. But if you look at this question, they do have this, A or B. So it always has to be A or B, A or B. Right, A or B, that's fine, we did do this. So A or B. So the question is something and. So something and something, or this one, okay? This is what we have. So this shall equal to A or B and C. This one and B and something or some, so and D and E inverse, or A or B and C and F inverse. And what's this? Something and something and something, or equal to something and all these and together. No, this and these two, so this will equal to B and C and D and E. This is same thing, right? A or B and C, F. Okay, what's next? So is A, B and something, A, B and something. So can we put them together? So it'll be A, B, something and something, or something and something. So this one we can combine A or B and C and D and E, right, this thing, or C and F. What's this? I have no clue what this is. A and B, or A and C. Yeah, that should be the same. So I can put this one here. So C and D, C and this. So this and this, also this and D and E, O, F. That doesn't help at all. I'm trying to unentangle this, but I think I get it more complicated. I have to get back. Let's get back to this. Think again. Well, so exclusive OR, things that are the same, when you exclusive OR them, they will become 0. Okay. The same thing, if you exclusive all them, they'll become 0. That could be a hint. For example, these two will be 0. These two will be 0. Right, so 1 and 1 is 0. 4 and 4 is 0. 0, 0 is 0. So we are left with 4 and 1. So it's 1, 0, 0, and a 1. That's why it's 5. Right? So now the question is, how many of these pairs do we have? And why are these two the same? Actually, it's this one and this one. Right? You see? 0, 1, 0, and a 1, 0, 0. These two are the same. Which makes sense. Right? So among all the different combinations, we have I, J, K. So I, J, K, I or J, and K. And J or I and K. These two are the same. And of course, I or K and J. And then K or I and J. And J or K and I. K or J and I. These 3 pairs will give you 0. Okay. But at each position, you can have all of them. And we have a large number, right? A large number of values. And you say we want to fit out this position, we want to fit out this position, we want to fit out this position. And for each position, we can always find its inverse. Yes. No, so as long as I, J, K are not all the same. You see, this is 1, 1, 1. This is a 4, 4, 4. Huh? As long as they are not the same. As long as there's one difference, right? If there is one difference. Actually, 1, 1, 4. That's only 1. Right? And it's by pure luck. Well, are these going to be a pair? We're talking about AAB, okay? We're talking about A or A and B versus B and B and A. Okay, so this is the same as this one, associative. And that's not what we're looking for. We want to look at distributive because it's always commutative, right? So distributive, so this one equals to B and A or A, which equals to B and A, right? B and A or B and A. And B, oh, A and A is just A. A or A is just A, come on. And this is B, oh yeah, they're the same. Come on. So this is just 1 and 4. This is 4 and 1, so it's exactly the same. And if the 3 are not the same, right? If this insides are not the same, then we can always swap them. Then we'll be the same, right? Yeah, because you have 1, 4, 1, we can get a 4, 1, 1. So whatever you give me, IJK, right? Whatever IJK you give me, it will have its pair. No matter what, it will have its pair because I and J can either be equal. If they're equal, then we can find the pair is, KKI, right? And if they're not equal, then we should swap them. So they're all going to be 0. So the only thing that we cannot find is if they're all the same. So we can actually try, just based on this observation, to see if it's gonna work. right? So what we're gonna do is do this and exclusive OR, right? Exclusive OR. What's 1 exclusive OR 0? What's 0 exclusive OR 0? That will be all the, that will always be 0. That will always be the same. So 1 exclusive OR 0 will be 1. Yeah, because it was 0, that's fine. So for I in range, n in nums, res exclusive OR, well, it's exclusive OR equal to this, then n. Oh, n and n. That's just itself. That's just itself. I'll return res. Five. 34. If this one's correct, then we're gonna submit it. I was trying to write it out. Yeah. Now I do believe this is the one. Yep. Notice that I, j, k is always equal to j, I, and k. Right? So when I and j is not equal, right? And when I and j is equal, when I and j is equal, so the only thing that cannot be cancelled, right, is ij is ij are not equal, right? So all the pairs are ij not equal. When ij is equal and k is not equal, notice that when I is not equal to j, this will always equal to this. When I is equal to j but not equal to k, then I, k is always equal to k, I. Thus, all I, j, k triplets, triplets can find its corresponding pair that would yield the same value, and exclusive all two same values lead to 0. The only I, j, k that will not be cancelled by exclusive all is when I equal to j equal to k. Hence, the solution, the answer, is to exclusive all everything in nums. That's a weird contest they have. All right, that'll be it. I'll see you guys tomorrow.